Hi, everybody. Welcome back to AWS on Air. I am Jordan Sullivan. I'm a developer advocate for Amazon Braket, which is our quantum computing service here at AWS. And today I am here with my co host, Nathan. Um, and also, we have a special guest from IBM Qiskit. This is Iskander Sitikov. Um, and today we're talking about a very exciting new launch in our quantum computing space. And would you like to give us a little intro about what that is, Iskander?
Okay, hi. First of all, hi everyone. My name is Iskander. I'm a also developer advocate, but in Qiskit side of things. Um, so today we're gonna be going through one of the special development we've been collaborating on, and this is Qiskit bracket provider. Uh, yeah.
Yeah. So just for the audience to kind of get things started, what is Qiskit? Tell us about it.
Okay. Yeah. So Qiskit is the quantum computing SDK, which allows you to run quantum workloads on a level of circuits, pulses, or algorithms. Qiskit came up as a suite of tools. We have core modules like Qiskit, what's called Qiskit Terra, which encapsulate circuits, pulses, algorithms, circuit libraries, and etc. All of the necessary things to do the core quantum development. And also we have high-level modules like Qiskit Nature, Qiskit Machine Learning, Qiskit Finance for related areas like biology, chemistry, finance, and machine learning, right? We also have low-level modules like Qiskit Experiments to run experimentation on a real quantum hardware. And we have special thing called Qiskit Metal, which is tool to design quantum hardware. Yeah, and
Whoa, wait, really? I was not familiar with that one. That's really
yeah,
cool.
yeah. So you should check it out.
I was I
I
was looking
will.
around on the Qiskit website earlier, and it looked like it was just a one-stop shop. I was seeing like lessons, guiding me through step by step, learning from the basics. It was like, what is quantum bits? What is the core concepts, all the way up to, like you said, these experiments. So it looked like
Mhm.
it's just a really one stop for me to learn about quantum computing and get hands on with it.
Yeah, exactly. That's actually true, and I'm the living example of it because I didn't know anything about quantum computing, and I started with Qiskit, and here I am. I work at Qiskit. So
That's the best
Yeah.
story.
yeah, exactly. So and
Yeah, no, I mean, I think a lot of people do learn quantum programming first from Qiskit. It's a real it's a fantastic entry point, and so many awesome modules and libraries that you can use.
yeah, thank you. And as a continuation of this, we have kind of also another level of stack, which is called providers, which is, I think, a great segue for our conversations today. So,
Yeah,
yeah.
so tell us more. What is a provider in Qiskit, and what does it do for me as a user of Qiskit?
Okay, uh, uh, so Qiskit is the hardware agnostic framework. We're trying to go with the agnosticity, and we have this abstract called provider, which is the entry point to access specific hardware or simulators for specific vendor. For example, we have IBM Q provider, which is give you access to IBM chips and devices. And now, because of this topic of our conversation today, Qiskit bracket provider, now we have a new provider which give you access to the devices that AWS bracket provides you to simulators and the local simulators too. So you can run basically you can run the Qiskit workloads on a hardware that bracket provides.
That sounds pretty awesome. So, if I understand correctly, you said hardware agnostic. That means I can use Qiskit to design a solution, to a problem using quantum coding, and now I don't have to implement like custom code for IBM, custom code for AWS. I can just switch out which provider I'm using, and I can try out this experiment in different locations with different hardware, different providers.
Exactly, you're exactly right. So there is like literally zero code changes. You just basically, instead of import IBM provider, now you do import Braket provider, and everything else remained the same. So that's the beauty of, I think, agnosticity. So you can bring everyone on the same plate, and I think it's good for overall for quantum ecosystem and for all of the players around.
Oh, I 100% agree, especially if I'm a researcher, or if I'm a student and I just want to try out and learn this topic without having to learn, the ins and outs of this cloud provider and this quantum device and that, that destination. Now I'm just learning one framework and using it no matter where it's actually going to be deployed and running.
Yeah.
So you've introduced the idea of the provider. Can we see it in action?
Sure.
Can you share a little demo of how it looks?
Yeah, let me. Yeah, if you just
right.
me or
there we go.
Tell me that you can see my screen and I can start.
Yes, go ahead.
Awesome. Again, this page we're gonna share it with you. This is just a notebook with overview of Qiskit Braket provider, of the main capability, which is just a short demo of it, just to highlight some specific things. Okay, we will be starting with importing everything, which is super boring part, but this you can get in any tutorial that Qiskit provides. So this is all import Qiskit. So one thing that you need to also import is the class package that we're talking about today, which is Qiskit Braket provider. It allows you to get Braket provider, which is giving you access to all of the hardware, all of the devices and simulators on a cloud AWS site. And also we provide Braket local backend to run your simulation on your local machine, which is maybe sometimes you need to just debug a couple of things, which is also useful. Okay, thing here that you probably might focus on is mapping between Qiskit and Braket and how this provider is actually working. So as I was mentioning, that we have this abstraction called provider, which give you access to specific backends or devices, and these backends can launch a job. So basically quantum workload in a cloud or on your local machine. And so this is basically direct mapping between Qiskit and Braket. So in Qiskit, we call this thing, this abstraction backends. In a Braket SDK, they are called devices. The workload that we launch called jobs in Qiskit, and in Braket it's called tasks. And again, so you have local device in Braket SDK, we have Braket local backend, AWS device, we call it AWS Braket backend. And that's pretty much it. That's just to lay down it in a brain, just to make sure that the notation is, you remember the notation.
Yeah, very helpful diagram.
Yeah, awesome. So now let's go through the code examples. I actually executed them here. So again, you import your Braket provider, you instantiate your provider. Each provider, no matter what the provider is, each provider exposes you a method called backends. You can call the backends. It will give you all of the providers.
So these names I'm seeing here, Aspen 10, Aspen 11, Lucy, I'm assuming these are the names of specific quantum hardware devices that I might be able to run my code on.
Exactly.
Yep,
yeah.
Exactly.
They,
so the first two are Braketti ones, and then IonQ, and then Lucy is the name of the device that Oxford Quantum Circuits has. It's also a superconducting qubit device, and the last three are Braket managed simulators.
Exactly. So those are familiar for you and for the audience. Those are the backends that are available for you. Also, provider allows you to, again, instantiate your local simulator or request for specific machine or specific device. So basically, the function here is just to get backend. You provide the name, it will give you a backend or device to run on. So same thing with IonQ, with Rigetti machines. Also, you can do filtration on the backends. For example, you're interested in devices that are online right now, which is probably a good thing to do. And it's option by default, by the way. And the types. For example, you're interested only in simulators, in cloud simulators, so we can do that too. And there's a bunch of options which are backward compatible with the bracket filtering logic. So everything here is like directly converts to bracket. So if you know how to filter search for devices through bracket, you can do that in here. So here, how you get access to the devices. I think next thing, which is interesting, is to actually how to run circuits right against the devices, which is important.
Definitely.
Yeah, exactly. So we have function called random circuits. It's a Qiskit built-in function which generates your circuit, just a random circuit with the you provided a number of qubits and the depth of the circuit and some seed of generation, and etc. So it will generate you a random quantum circuit, and in order to run your circuit against specific device, Qiskit has a notion which called transpilation. Let me actually quickly describe what it is. So different devices might have different connectivity maps, which means different gates, different connectivity graph, and all of this information you can get access in AWS Braket website, because devices expose their connectivity maps, error rates, and etc. for the gates and for the devices. So different devices has different connectivity maps and maybe error rates between gates. So for the gates, so you might be interesting to compile your circuit for specific device to be able to run it in the most efficient way. So we expose this function called transpilation. You provided a circuit and you provided backend, and it will recompile this circuit into equivalent one, but with the optimal amount of gates, so you don't have like expensive swaps and etc. So it basically give you equivalent but better circuit. So once you get the circuit, you can just call method run. So you have device, you execute method run, you pass the transpiled circuit, and specify number of shots that you want to do on this device. So you get the job ID back. You can retrieve this job or just wait until it's finished. Depends on the queues for the hardware. It might take some time, so you want to probably retrieve the job out of the queue. So you again have a function for the devices called retrieve jobs. You give it like job ID, job ARN, or maybe you have it somewhere in environment variables. Yeah, basically you get the job and you want to like, get the results, right? So results probably it's like counts or some quasi probability of specific states. And so in Qiskit, we have one of the modules in Qiskit is visualization. So we provide multiple functions to visualize the states of the system or result or probabilities in that case. So we just called plot histogram on the results of the execution of job, and we get our plot back. So this is kind of short walkthrough on how to run circuit against hardware. So again, you select your device, you transpile your circuit, you compile your circuit for this specific device, and you run it against it. That's pretty much it.
That's pretty awesome.
Nice.
Thank you. Okay, maybe I should jump on even more interesting thing, which is running algorithms.
Yeah,
So
do it.
yeah. Okay, we can run circuits on devices, but as time goes by, the new algorithms are popping up, and one of the most popular algorithm, which is called variation quantum eigensolver, which is again variational algorithm to optimize your circuit, like optimize parameters for your circuit to get the eigenstates for your problem, right? So
yeah, so this is like an early stage quantum application for this like noisy intermediate scale quantum era that we're in right now. So it's a quantum chemistry generally algorithm.
Exactly.
So if I understand correctly, I'm trying to find exactly what those magic numbers are that plug in at the start. Those floats right there.
Oh yeah, just
looks like a high precision number there.
yeah, it's high precision number. Basically, it's a operator for H2 molecule. So this is how it looks in a poly notation. For those folks who know the physics, probably know what the poly notation means. So this we basically define the again, this everything is in Qiskit built in. So these polys are, we imported them in the beginning. If you want to look at they're gonna be in the beginning in the first paragraph of this notebook in the imports. So we basically formulate our operator, and we, as you might know, that for the BQE you need some circuit to optimize parameter of and the operator, right? That you're gonna be getting eigenvalues for. So what you need to do is to again define your problem, define quantum instance, which is a wrapper around our backends or devices. You call it anyway. So in that case, I'm using local simulator just to showcase quickly how it runs, and it will be in a second because I didn't put any iterations in here, but you get the point. So this what this toLocal is. This toLocal is the, again, as I was saying, we have the circuit library. This is one of the built-in circuits. You can look on them if you want. Probably, maybe I can show it. I don't know. Local to instructions. Okay, let me skip this part.
Yeah, that's cool. We can just move on.
Yeah.
So yeah, Iskandar, can you talk a little bit about how this plugin was or this provider was developed? What was the process there?
Okay, so the process was in Qiskit we have what's so called many programs, and one of these programs called mentorship program. We have Qiskit advocates who are spread around the world, and each year, twice a year, we launch a mentorship program, which is 3 months long program to work on problems of quantum computing and maybe research or development, etc. So I'm one of the mentors of this on this program, and my project proposal was to develop Qiskit Braket provider. So I've proposed this idea, and I got the team of mentees, and for the last couple of months we've been working collaboratively with Qiskit mentorship and folks from Braket in order to provide this utility for the developers and researchers. So we started in March, and we're more than 2 months in. I think we have around a month until the end. We already reached MVP stage for this Braket, so it's stable. You can run your workloads. For the following months, we will be working on improvements, adding new features, and etc. So yeah, that's
now when you said collaboration, I'm assuming this is all out in the open. There's a GitHub repo somewhere.
Yes, exactly. So actually, so because Qiskit is open source, and we're trying to be pro open source to make science and development and programming as open as possible, so it should be accessible to everyone. And this plugin is not any different. So yeah, exactly. We also do it in open source fashion. You can go ahead, and I think links will be provided. You can go ahead to the plugin page. It has all of the instruction how to start. It has this tutorial that I'm showing you right now. You can check everything that is happening in the issues. So we have everything open. So our roadmap, you can check our roadmap and new development in the issues. So even the roadmap is open. So you can, and because it's open source, that's a great opportunity for everyone who wants to jump on quantum computing, jump on the development. So and be familiar with not only one framework, whether it's Braket or Qiskit, it's like a collaboration between. It's like you basically jump in on it, you know the two things at the same time.
Yeah. I mean, on the Braket side, we're very excited about this plugin. It's like our most requested feature from folks who want to run on Braket. Qiskit is a great framework, great SDK, and I think people are going to be really excited that they can run on ion traps and superconducting qubits in UK, in the US, on quantum annealers, all just using their familiar Qiskit framework. So yeah, thanks so much for coming. Oh, and I do want to mention, of course, this is very much, we're very passionate about education and about helping people learn quantum and helping people do research on quantum computing. And to that end, AWS has this credits for research program. So if you're interested in running an experiment on a quantum computer, you can just submit a short application to our credits for research program, and we'll also have links for that. And you'll be able to apply to be able to run on a real quantum computer.
Fantastic.
So, yes.
Well, this makes me super excited. Thank you so much for showing this.